sharing this session. The first speaker of this session is Kohei Kishida, and his talk is about topology and justified through belief. Reflect, evidence-free, and pointless approach. So, to this one.
Okay, yeah, thank you so much for this opportunity to give present this talk. So let me start from introducing a bit of a bigger picture than this entire talk, so that it'll be clear to you what I'm supposed to be doing in this talk. So this talk is about this talk is about the epistemic logic, and the epistemic logic's fundamental question is, well, original fundamental question is, what does it mean to say that the agent alpha knows that phi? So logicians introduce the model operator case of alpha for alpha knows that, and then approach the question above either axiomatically or semantically. So axiomatically means that they paraphrase the question into what inference rules and axioms govern this model operator, or semantically, they mean what semantics does this model operator have. So those two questions are not the entire, actually tied closely together, not separate at all, because of the correspondence results that connect these two questions. For instance, look at those two bullet points there. On the one hand, you have this axiom, and on the other hand, you have this semantic condition that this alpha epistemic alternative or accessibility relation among possible worlds being reflexive, and those are connected by correspondence results. So if one endorses one of those two, then they must endorse the other. Okay, so that's on the one hand. But on the other hand, if philosophers or logicians try to justify their formalism, then they may take axioms first or semantics first in the order of justification. For instance, to take an example of a semantics first approach, some, especially theoretical computer scientists and working on the distributed computing or multi-agent systems, adopt as reasonable semantics something called a partition model sometimes, which partitions the set of possible worlds into cells of worlds that the agent alpha cannot distinguish, so that the epistemic alternative relation among worlds, in this case alpha indistinguishability, is an equivalence relation satisfying the reflexivity, transitivity, symmetry. So they sort of introduce this as hey, this is a reasonable model, right? And then after that, these semantic conditions justify logic S5, which is made of the axioms corresponding to 1, 2, 3, for instance, T axiom there, 4 axiom, 5 axiom there. Okay, so this is this is one example of a semantics first approach. There's also an example of an axioms first approach. So, for instance, some philosophers, especially, argue for or against axioms by reflecting on those axioms directly. For instance, when Hintika originally introduced epistemic logic, he argued for a logic S4 consisting of axioms T and 4, and argued against axiom 5. Or Timothy Williamson in 2000 argued against axiom 4. Those are examples of axioms first approach. So the topological approach, which is something for which I propose a new version today, is a semantics first approach from which S4 arises. So usually when people try to establish or justify S4, they take those S4 axioms like T or 4 first, rather than talking about, hey, why it has to be, why the relation has to be transitive. I mean, look into the epistemic alternative relation and think about transitivity, you usually don't get anything out of it. So first you justify axioms, and then those axioms are going to give transitivity. But today I'm going to give the opposite approach, in which I'm going to provide a reasonable semantic structure first, and then from which S4 arises. Okay, so that's this is the bigger picture. So let me get to first reviewing the conventional so-called evidence-based approach in the topological semantics for epistemic logic. So excuse me. So the topological semantics for epistemic logic is based on a certain idea that knowledge is justified through belief, which is a kind of old idea from the ancient Greek philosophers. So how does it go? Let me review the formal setup first. So here's the definition of a topology. If you do not know it, then let me just briefly cover it. So a topology on a set W, I mean, we usually consider that as a set of possible worlds, is a family of subfamily of the power set. So it's a family of subsets of W that is closed under finite intersections and the arbitrary unions. And elements of this family O are called open sets of this topology. And then the topology comes with its interior operator defined in that way. So taken given any subset S, the interior of S is the largest open subset of S. And then, given this formal setup, epistemic logicians find some significance in the following fact, namely, when we have a family of subsets of W that is closed under finite intersections, then if you take the set of all unions of any family of elements of this family B, then it forms a topology, and moreover, there's this condition star there holds, namely that let me read it in a possible. So this point W is in the interior if and only if you can find some element B of this family big B that says that so to speak, W is well within this subset S. I see some. I keep hearing some like beeping sound, but I don't know. Anyway, so when this sort of thing happens, one describes this situation by calling this family B a base that generates this topology O. But the point is that the B is kind of taken arbitrarily. It's just, I mean, its only restriction is that it is closed the finite intersections. But if you take all the unions of all the elements, just close B with taking arbitrary unions, then it generates a topology. So what's so important about that? Well, the key idea of the topological semantics for epistemic logic is that in this condition star, you're going to read this element B from this family B to be some kind of a piece of evidence that justifies this proposition S, so that the interior operation interprets a justify the true belief. So let me spell out how exactly it goes. There are actually two styles in this semantics. So let me first take this sort of a style from the school of evidence logic, in which the logicians interpret this statement or model operator alpha knows that with this interior operation, and then read this family B or base as the set of propositions that correspond to pieces of evidence that the agent alpha has, which gives us the rendering of this star condition as follows. Namely, on the left-hand side, alpha knows that phi or alpha knows that phi is true at the W. And if and only if on the right-hand side, the agent alpha has a piece of evidence saying something that is true, one, true at the W, and two, entails phi. So this is a one idea of one notion of justifying or evidenced true belief. So when alpha knows that phi, it means that there's an evidence that justifies phi. Sorry, is someone asking a question? I heard something. No, it doesn't look like it.
No, we don't think so. Please continue.
Excuse me?
Well, there is no question so far. So
Oh, okay. Yeah, sorry about that. And actually, it's been like 10 minutes. Okay, wow, I'm very slow, it seems. Right. So okay, so that's a one school, and then there's another school called a formal learning theory, represented by or in the style of a Kevin Kelly, or also a topology via logic in the style of a Abramsky and the Steve Vickers. This family D is regarded as the set of observable propositions, and the interior operation interprets it is verifiably true that, so that the star condition above reads as follows. It is verifiably true that the phi is true at the W if and only if some observable proposition that entails phi is true at the W. So this makes the set of this topology O, the set of verifiable propositions, meaning that the propositions that are verifiably true if true. So important thing is that in both styles, the interior operation interprets a version of justified true belief. And then one additional fact is that the resulting logic of this semantics is S4, because S4 characterizes interior operations. Okay. I don't know. Given the time constraint, I may skip this example, because it's a review of its example about the review. So let me go to the yeah, it's been 13 minutes. So let me get to my proposal part. So my proposal is as follows. So far, I just very briefly reviewed the version of a topological semantics in which we read a base generating a topology as evidence justifying knowledge. So that's why we may call this approach a evidence-based approach. On the other hand, in the alternative approach that I'm going to propose today, we generate a topology using something else rather than base, so that knowledge is justified differently, other than by evidence justifying knowledge. So that's why I call this approach a baseless or evidence-free. So let me go through. Let me give you sort of a central idea of how the formalism. First, how the formalism works. So let's say review the evidence-based approach again, massaging the definitions we saw there. We can actually
interrupt you. We have a kind of technical trouble, so could you wait for a couple of seconds or minutes? We are very sorry about that.
Oh yeah, that's okay.
Can you hear me?
Oh yes, I can hear you.
聞こえます？
Yes, I can hear you. I can hear you, but can you hear me?
Yes, but there is a machine trouble on this side, maybe. So could you please pause for a moment and resume?
Oh, yeah, sure.
Okay, so we are.
Yes,
I think our staff is.
I will resume whenever you're ready.
Resuming
give me a cue.
well, yeah.
Yes. And like, should I go back a bit or something?
A bit,
like that?
yes. From the maybe the yeah, like that point.
Okay. So I will resume from the beginning of the current slide.
誰の PC？
こっちはこっちでトラブルが来たな。It's okay. It's okay. It's okay. Leo, it's okay. No. 今、機械のトラブルで待ってもらってんの。それはちょっと。Yes.
木田先生。
はい。
聞こえます。
聞こえます。
今見えてますよね。OK。
見えてます。トラブルもう解消されました。
はい、続けていただいて大丈夫です。
はい、すいません。ちょうど息子が入ってきたところだったんで、よかったです、ちょうど。何分ぐらい、あと時間あるんですかね。私。
この1回止め。12分ぐらいからスタートしてます。
12分ぐらい。12分ぐらい。OK。
はい、表示されてるまま。
これ見てないんだと思う。
多分12分45秒です。
それがあるってことです
か。そこで止めてくださってたんですね。わかりました。じゃあ、そこから、始めます。わかりました。すみません。いいですか？
もういいですか？タイムキーパーのあれって見えてますか？ちなみに。すいません。
12分45秒っていうのが見えてますが。
はい、そのままでお願いします。
はい。
これがタイムキーパーです。
わかりました。はい、すいません。では。はい。始まった。Okay, all right. So, that's so where was I? Okay, so here's me presenting a new proposal. So on the one hand, we reviewed this version of topological semantics in which logicians read a base generating a topology as evidence justifying knowledge. But in the alternative approach I propose today, we generate a topology using something else so that the knowledge is justified by something else than evidence. So that's why I call the first approach, the conventional one, evidence-based approach, whereas I call my approach baseless or evidence-free. So let me briefly massage the definitions in the formalism of the evidence-based approach, so that we can sort of get regard what they do in the following way. So what they do is to start from a base and then generate an interior operator using this way, so that the interior is the union of all subset from the base. So then after that, using that interior operation, they obtain a topology as the set of open sets, where we define the open sets using the condition on the right there, namely use open if and only if it is a subset of its own interior, actually equals the interior. But anyway, the key observation for the formalism of my approach is that this second construction of obtaining a topology using the notion of open set actually makes sense for any monotone map and not just the interior operations. So the upshot will be that instead of taking the step 1 and step 2, I'm going to take a step 2, apply to a monotone map, and then take step 1. So as follows. So this is the step 2, first take from any monotone operator triangle, generate a topology. I mean, we can just define the notion of open sets there, generate a topology as a set of open sets. And then from this topology, we just obtain the interior operator in the usual way. And actually, this construction to prime there indeed generates a topology, so that works. So here's the commutative diagram showing what kind of things is going on with these constructions. But anyway, So that's formalism. So let me get to the interpretation or epistemic interpretation of this formalism. So this construction we did of a interior operation from any monotone map means this dagger condition there. And this condition is just, this part highlighted in green is the same as in the evidence-based counterpart we saw before. And the only difference is this red part. While this we had U is from the base, we now have this condition that the U is an open set, meaning that the U is a subset, or U entails diamond U. So what epistemic significance can we give to this red condition is the next natural question. So here's my proposal. Here's my answer to that question. So let's read a triangle as alpha believes that, and then this openness condition entails alpha believes that U as this proposition U having the property that its truth induces alpha's belief. So for instance, propositions corresponding to observation, for instance, a coin toss has come up heads, may arguably be belief inducing, because if it is true, then the observer can just observe it and form the belief that it is true. Okay, then this dagger condition just reads as follows, namely, alpha knows that phi at the W, if and only if some belief-inducing proposition that entails phi is true at the W. So in short, this interior operation now interprets a justified true belief of the kind we may call induced true belief. So let's say compare how these two approaches, the conventional one and mine, work using a kind of a simple example. For instance, there we take three worlds W1, W0, W1, W2, and the proposition a cat ran across the yard. That is true in W0. That is not true in W1 and W2. So in the evidence-based approach, we set this proposition to be in the base, namely corresponding to some evidence for one reason or another. Then it makes it the case that they actually in W0 and in no other worlds, the agent knows that a cat ran across the yard because this formal condition is met. Okay, and namely that they are in W0 and only in W0, it is the case that you find the evidence that entails a cat ran across the yard, and that is true. And rather similarly, to some extent similarly, in my evidence-free approach, alpha is going to sort of give the same truth value to the knows that, but in a slightly different way. Namely, in the evidence-free approach, we start from assigning alpha some belief, maybe justified, maybe not justified. So for instance, alpha may believe that if phi is the case at W0, but also W1, because in W1, wind blew a plastic bag across the yard or something like that. So this makes but still, this makes a phi belief inducing, because still, as you can see from the diagram, a phi entails the belief. So then alpha knows that the phi in W0, but not in W1, because you actually do not find a belief-inducing U, belief-inducing a proposition that actually is the case in W1 and entails a cat running O5. Okay, so that's the how the semantics works. So I do not have much time left, so let me go quickly on how logic of belief and induce the true belief works. Or actually, what's the logic of this new approach? Okay, so there's a big contrast between the two approaches. So in my approach, we have actually two model operators, namely belief in addition to knowledge. So its logic can actually, one, describe the primitive component of semantics directly, and two, describe the relationship between belief and knowledge, and not just knowledge, property of knowledge, but actually belief and knowledge, as where we understand a knowledge as induced true belief. So that's the actually sort of the advantage I'm going to for which I'm selling this new approach. So this logic can, I mean, speaking formally, this logic can be axiomatized using the following theorem that they look, when triangle is any monotone map, then the interior operation given by that is the unique function satisfying these axioms. So you can just give a axiomatization logic using these axioms and rules. So what do they mean? Well, they mean that they they imply, for instance, box is monotonic and obeys logic test 4. So yeah, well, okay. It also satisfies it also entails the following axiom. So combining 3 and 1 and the 4 there, I mean, you can kind of see that they respectively state that box is an induced, as in 3, and not true, I meant true, as in a 1, and then it's a belief, as in 4. So that's how it works. So let me close with the 2 remarks. So one remark is that everything so far can be done in a pointless or point-free logical fashion, replacing power sets with the complete lattices. And once you do that, we have a completeness and soundness theorem with respect to not only power sets equipped with a monotone map, but also complete lattices equipped with a monotone map. So that's a sort of the formal results I have about this logic. So anyway, so appendix, I mean, I don't have time, so let me skip. So let me conclude and say something about future work. So, well, actually, this is just a summary. I mean, what I have just done is to introduce an alternative approach to the evidence-based approach, namely an evidence-free approach, baseless evidence-free approach to topological semantics of epistemic logic. Its core idea is that they to take advantage of the belief-inducing property of a proposition U as a criterion of this proposition justifying beliefs. So this gives us some notion or some axiomatization of justified true belief, and indeed we have introduced, or we sort of derived, a new logic of both belief in addition to not just a justified true belief, but also belief and justified true belief, the relationship thereof. So that's a summary. About the future work, we may investigate how to refine this semantics so that the box behaves more like properly or suitably as knowledge. So this may include searching for, say, axiomatically for additional axioms that make a box satisfy more desirable axioms, or semantically additional structure in the semantics that makes it more reasonable to interpret this openness or belief-inducing property as a belief induction properly, for instance, avoiding Gettier-like cases. You may actually, okay, anyway, that's, okay. Thank you. So thank you so much for your attention.
Thank you very much. And we have 6 minutes question and answering time. And those who have the questions, please come over here and use this mic so that Kohei can see you. If there are any questions, yes, please. Come over here. Look at the camera.
I have 2 questions. Two questions.
Yes.
One question is it is not clear to me your induced true belief and justification. One question. The second question is, do your explanations contribute to Gettier station? This is second question.
Okay, can you repeat the first question? My connection was not quite good. So second one I got. Yes, I got it. But can you repeat the first question, please?
Your explanation of induced true belief, can is relation to justification. Just what we believe. Justification. What you induced to belief can contribute to explanation of justification. What kind?
Okay. The most kind of a crude kind of a induced sort of a belief induction is like if you look at the say sense data theory, then that's a I mean that's the most crude kind of belief induction, right? They thought that the sense data can be a basis of epistemology because there's a direct connection between sense data and belief in I saw something red, and then that I mean I see something red, and that's going to induce a belief that I saw something red, and they thought that that's just at least that justifies that belief, and so on. And also not just sense data, but also Quine had this stimulus, belief forming stimulus, and so on. So what I kind of intended was to sort of not axiomatize, but
岸田さん、またちょっと止まってしまったみたいで、
わかりました。すいません。
ちょっと3分ぐらい、30秒ぐらいお待ちください。
わかりました。聞こえてはいるんですか、僕の言ってること。
聞こえます。今聞こえますか？
はい、聞こえます。聞こえます、聞こえます。
今、復活した。
あれなんかタイムキーパー進んでるので、もうやることになってるのか。ポーズ。すいません。
今、じゃあ、また続き、じゃあ、お願いします。
もういいですか？
大丈夫です。こちら聞こえました。
Okay. Yes. So I don't know how much I need to rewind, but let me sort of just give a kind of a concluding part. So there have been like a sense data theory or Quine's sort of stimulus causing I mean belief causing stimulus and so on. So what I kind of wanted to throw in by this belief induction was to sort of give a kind of propositions that correspond to observation and so on, so that it can be a basis of a justified true belief in such in sort of a way they had in mind. Of course, that whether it is going to, so getting to your second question, whether that's going to avoid Gettier-like cases or not is a well, actually, yeah. I mean, any epistemic logic when in a sort of a its bare bone. No, it doesn't come with the good enough structure to deal with the Gettier-like cases, but it doesn't mean that you cannot add a lot of the extra structures, like I say in this future work part B. You may sort of this may be a framework on which you can add the extra structures to the semantics, so that you can talk about the genuine causation as opposed to just like coincidental belief induction and so on.
Yeah. I see. Thank you.
So I think there is time for one more question. If there is no questions, one short question from me. Okay. So what you're talking about
So sorry, I cannot hear you now. For some reason, I don't know why. So you like started your
すいません、
question,
ま
but
た
then
エラーで止まってしまってます。 すいません。
せん。
なんか
いえいえこっち
阪大の会場の Wi-Fi が止まってるみたいです。
ああ、それは。
ランないんですか？ちょっ
It
と
seems that
すいません。
Wi-Fi in this room is dead, so we should use maybe the able.
エディロームつなげます。あ、つないでます、これも。こっちで。これ入れますか？これエディロームですか？それエディロームつながってます。あ、これじゃない。どれズーム？多分一応だからエディロームつながってズームどれ？ズームこれ？あ、どこ行った？どこ行ったの？あ、こっち映ってる？ズームどれ？全部消してる。あ、ズームあれだって2画面。声入ってますか？
はい。僕にですか？僕。
あ、これが映っちゃった。
すいません、また切れちゃって、再開しても大丈夫ですか？
とりあえず一旦大丈夫です。多分。聞こえない？
聞こえてますよ、さっきから。多分全部聞こえてたと思いますけど。
こっちに繋がってない。
聞こえますか？
はい、聞こえます。聞こえますか？
このパソコン良くないかも。
ちゃんが大丈夫です。
ごめんなさい。
Okay, can I continue the question? So we have only
モニタリングしてるんで大丈夫です。
Okay, Kohei, can you hear me?
Yes, I can hear you. Well, actually, I can hear many people, but I can hear you too.
Okay. So my question is there a possible connection with topological semantics of yours and the type theoretical semantics like dependent type theory?
Oh. It's actually.
So the topology reminds me of the context of the type theory. So there could be a connection.
Yeah, that's I mean, if I say yes, then that's a very distant connection and actually a very ambitious one. I hope it's my long time goal to connect the topological semantics of a agent's beliefs or sort of epistemic logic with a topology in computation, because many things in actually it's kind of interesting that, for instance, when we talk about sort of this sort of observability in the way formal learning theorists and some theoretical computer scientists like Abramsky and Vickers do this sort of thing. They really have computation in mind. For instance, this sort of connects like epistemology with, for instance, halting problem or other phenomena in, sort of unobservability results in computation. So I'm not entirely sure if this goes directly to a type theory, but my sort of one of my research ambition is to connect this sort of a topology to topology in computation, like homotopy type theory and so on. Well, homotopy type theory, or say distributed computing. Oh yeah, anyway.
Okay, can we finish the session? And let's thank the speaker again.
Thank you so much.